When we think of lunar exploration, we usually think of this. 6 Apollo missions landed in the same general type of environment, the brightly lit, relatively flat equatorial region. We spent the 20th century exploring the moon's sun-drenched front porch. Artemis 3 is targeting a completely different world, the lunar South Pole. Because of the extremely low sun angles at the poles, the light here is perpetual twilight, casting long, jagged shadows across a landscape we have never seen from the surface. This geometry creates permanently shadowed regions, or PSRs. These have craters where the floor hasn't seen a single photon of sunlight in billions of years. Temperatures here are so low that they act as cold traps, freezing water molecules and solar wind particles into the regolith like a time capsule. These dark craters are frozen vaults, holding the chemical history of our solar system in a perfectly preserved, undisturbed state. Getting into those vaults requires a shift in mission design. Artemis 3 isn't just a visit, it's a heavily equipped scientific expedition built for active fieldwork in the most extreme environment we've ever faced. Every action the crew takes is dictated by this document, the Artemis 3 Science Definition Team Report. It's the master playbook for the entire surface day. The report defines 7 overarching objectives. The crew must decode planetary processes, analyze the origin of polar volatiles, and observe the local space weather and the distant universe. These goals collapse into 2 core pillars: using the lunar record to understand our past, and mitigating the risks of future deep space travel. By following this playbook, Artemis 3 marks the point where human presence on the moon becomes a permanent platform for complex planetary science. During Apollo, astronauts on the surface were relatively isolated from the scientists back on Earth. Communication was limited, and the crew relied on pre-planned checklists with very little real-time scientific debate. Artemis utilizes a different paradigm. The astronauts are trained geologists, acting as real-time extensions of an Earth-based science team. They will be in constant contact with experts who can see what they see and help them make immediate tactical decisions. This enables in situ triage. Instead of collecting every rock they find, the crew uses handheld instruments to analyze a rock's mineralogy on the spot, ensuring only the most valuable data makes it into the bag. The need for triage is driven by strict physics. The lander can bring 100 kilograms of tools down to the surface, but it can only return a maximum of 35 kilograms of samples to Earth. Because return mass is so limited, every ounce of rock must be selected to answer specific questions about the origin of the moon and the solar system. The sampling toolkit is designed for variety. The crew will collect large hand samples from boulders to date impact events, and they will push metallic drive tubes deep into the soil to capture the vertical layers of ancient lunar history. They will also perform paired sampling, collecting material from inside a dark, permanently shadowed region and comparing it directly to a sample from the sunlit area just a few meters away. But the biggest challenge is keeping those samples intact. In the 1970s, an unsealed moon rock reacted with Earth's atmosphere on the flight home, rusting the sample and altering the very data we were trying to study. Artemis 3 uses double vacuum-sealed cryogenic containers. These are designed to keep the ice and volatile gases at their original lunar temperatures for the entire trip back to a laboratory. If the temperature of these samples rises even slightly, billions of years of pristine volatile data will simply evaporate. Maintaining this cryo-chain is the mission's most difficult technological requirement. Once home, these samples allow us to refine the cratering chronology for the entire inner solar system. We can use the moon's timeline to accurately date the surfaces of Mercury and Mars. But there is also a practical goal: in situ resource utilization, or ISRU. By extracting the hydrogen and oxygen from lunar water ice, we can create the consumables needed for a long-term stay. This process provides breathable air for astronauts and liquid rocket propellant for spacecraft. Robotic scouts like the Viper rover will map these deposits first, providing the ground truth needed for humans to begin large-scale extraction. By harvesting these materials on-site, the mission demonstrates how we can sustain deep space exploration without being tethered to a constant supply line from Earth. The final objective is understanding the human cost. Artemis 3 will measure how the moon's partial gravity and deep space radiation affect human physiology over the course of a week. Scientists will study how human microbial flora reacts and adapts in this environment, data that is vital for keeping a crew healthy on much longer journeys. These survival metrics are the mandatory prerequisites for a human mission to Mars. Every procedure tested on Artemis 3, from the cryogenic seals to the real-time geology, is the operational architecture required for a Mars landing. By validating these survival techniques in the shadows of the South Pole, NASA is building the specific tools needed to sustain human life across the Martian horizon.